Yeah, so my name's Ian. I'm with USRA here at NASA GRC, and I'm going to talk about flow of granular materials in micro-G. So next slide, please, Marie. Yeah, so a little out of place in so much as I mostly do modeling, but it's going to be a little bit of an experiment today. And we're also less interested with PSI so much as we are with ISRU. But it's still about granular materials. So specifically with granular materials, what we're interested in is the jamming transition. So both on Earth and also out in space, famously with like the OSIRIS-REx mission, the jamming transition between a granular material behaving statically to behaving dynamically can cause all sorts of problems. And we essentially just want to understand how that transition depends upon material properties and on the external gravitational condition. So next slide, please. So yeah, the motivation for this is mostly this experiment on the lower left-hand side, which flew in the ISS last year, or maybe a couple years ago, but was published last year. So they have this hourglass, it's pseudo 2D, it's filled with various types of regolith simulant, and then they flip the hourglass and they look at the flow profiles that you see of the simulant through the hourglass in the throat, and they map that on to certain laws like Beverley's law and find that it fits within certain correction parameters. So we're interested in the same thing, but we want to study that static to dynamic transition. So set up this model, which is a very simple MD model. So it's a particle-based model. It's a 2D funnel filled with a monolayer of polydispersed spheres, and the funnel is initially plugged, and then you unplug the funnel, and you watch whether or not the spheres flow out. So next slide, please. So within this very simple MD model, we choose a very simple particle force model for how these grains interact. So we follow the DMT, Duryagin, Mueller-Toporov, I believe, model. So the force between any two particles is simply a combination of a normal and tangential force. The normal force is a combination of a normal spring, a dashpot damper, and then this approximation for the van der Waals force between two particles at contact. And then the tangential force is the same set of things, but with this Coulombic friction criterion. So basically, there's 4 key variables here. You have K, gamma, mu, and phi. And K, gamma, and mu are pretty easily determined from material properties, but phi within this model is less so well determined. So it comes down to essentially trying to figure out what is the appropriate phi for this sort of simulant that we're interested in. So next slide, please. So the procedure that we have is there's this funnel, right? It's 2D. It's filled with 1,500 of these polydispersed spheres with a polydispersity index set by the simulant we're trying to model. The spheres randomly pack in there. It's plugged. Remove the plug. Watch it flow out. So these should be movies, but I don't think they'll play, so we can just move on and keep going. Next slide, please. So to calibrate the phi within this model, we do this essentially like tiny version of that ISS experiment. So we have an hourglass. It's laser cut from acrylic. We fill it with this simulant called Mars Wind Drift that we have here at GRC. It's essentially a low cohesion material that they use to replicate the Lunar rover environment when it tends to sink into sand dunes. And the nice thing is that it's perfect spheres. So it's much like what is in my model. So what we do is we fill this little hourglass with the simulant and then do particle velocimetry to see what the profile is like through the throat of this hourglass as we flip the funnel in 1G. So next slide, please. So yeah, so here we have the comparison between experiment and simulation just to set this phi variable. So in the top, what we're doing as we go from left to right is we're changing the size, the throat of that hourglass, and you see that the flow profile transitions from this noticeably parabolic or arch style flow profile to more of a plug style or even just completely flat flow profile. So this is pretty much expected for any low cohesion material sort of flowing in this sort of hopper style geometry. And then in our model, if you choose the appropriate phi, you get kind of the same transition with changing funnel geometry size. The thing that's important here is that if phi, for example, in our model is too large, nothing flows at all. And if it's too small, essentially it's just always that sort of plug style flow. So it's only in this certain close regime where phi sort of matches what we see in the experiment. So next slide, please. So with that, we can then sort of extrapolate in the simulation to what this simulant would do if we go to different gravitational conditions. So I don't think either of these movies will play, but on the left-hand side, we have the G=1 case, in which case all these grains just kind of flow through this funnel, sort of as you would expect a dry sand to. Whereas, again, this is the exact same type of simulant, same phi setting, all those other variables are the same. But if you go to the lunar gravity case, they don't flow through that funnel at all, it clogs. So next slide, please. So since we're interested in that clogging, that jamming transition, we are looking at the flow profiles instead in this throat region. We're looking in this upper region up here. So next slide, please. And what we get is essentially, we can construct this sort of matrix. It's like a phase diagram of the flowing versus jam behavior. So within this large plot, it's all these subplots are different simulations performed at different G and different phi. So in the top left-hand corner, we have the G=1 case and phi being very low. You get these kind of arrowhead shaped plots, which just means all the grains are flowing through the funnel sort of as you expect. They have this shape just by the geometry of the funnel. But as you increase phi, you hit some critical point where essentially this arrowhead starts collapsing and the whole funnel clogs. And then as you decrease G, so you move down this diagram, that critical phi also decreases. So you get this sort of, upper left-hand triangle sort of shape between what flows and what jams. And then as you, next slide, please. And then just to sort of show the robustness of this, as you go to even lower gravity and and therefore also lower cohesions, the same sort of phenomenon occurs. So I'm seeing some questions in the chat. I'll try to answer those as they're coming in. Yeah, so we have looked at the Tabor parameter and JKR versus DMT. It is slightly different, but honestly, in regard that we're going through phi and G like multiple decades, it's a pretty robust behavior that we're seeing. So we're pretty confident in this. Also, not included yet because it's a collaboration with some people. There's some experiments done in a drop tower with regolith like JSC1A, and they observe pretty much the exact same thing happening. So these are just preliminary results, but we're pretty excited with them. Next slide, please. I think it's the last one. Yeah, so thank you. These are acknowledgements to the funding, and then also people who helped. Dr. Amin, a former postdoc, Satya Muru is an intern from UT Austin, and then the lead scientist is Dr. Suman Sinha. So that's it, and it was actually pretty fast. So I guess if there's any more questions or if I missed any, please feel free.